Welcome to Study Loop.
In this problem, we're using concepts such as bond energy and energy dissociation to find things such as wavelength, kinetic energy, and excess energy. And these are really useful skills because we're dealing with the same concepts in chemistry over and over. And a huge concept of this is energy. We want to know how an energy is going to be favored or not favored in a reaction and what conditions we can use in order to create the energy we want. So for part A, we're told that the bond energy of HI is 295 kilojoules per mole, but we can convert that to say that that's the same thing as saying 295 times 10 to the third joules per mole. Now remember, for part A, we want to know the longest wavelength that is possible. To find wavelength, we can use this equation, which says that wavelength, lambda, is equivalent to n times h times c over delta E. Now, n is Avogadro's number, h is what we call Planck's constant, c is the speed of light, and delta E is simply the bond energy we found before. So lambda, the wavelength, will be equal to Planck's constant, 6.626 times 10 to the negative 34th joules seconds, times the speed of light, 3 times 10 to the 8th meters per second, times Avogadro's number, 6.023 times 10 to the 23rd. We'll divide that by our bond energy, 295 times 10 to the third joules per mole. We can say that then lambda, once we simplify, is 4.06 times 10 to the negative 7th meters. But when we're talking about wavelength, we like to use nanometers as our unit. So we can convert that, to say that lambda is 406 nanometers. So that is the longest wavelength of light that we can use to maintain the energy dissociation bond. And now for part B, we're told we have a different wavelength, and we're told that it's 254 nanometers, and we want to find the excess energy. So the first thing we can do is find the energy of the photon that's making this wavelength possible. And to find the energy of a photon is equivalent to hc over lambda. So we would take Planck's constant, 6.626 times 10 to the negative 34th joules seconds, times the speed of light, 3 times 10 to the 8th meters per second. Then we'll divide that by our wavelength in meters, 254 times 10 to the negative 9th meters. We can simplify that to say the energy of our photon is 7.83 times 10 to the negative 19th joules. And then we need to find the energy that would cause this to dissociate. So we take our original bond energy and divide it by Avogadro's number. And we find that we have the bond dissociation energy of 4.898 times 10 to the negative 19th joules. And then how do we find our excess energy? We'll take the number or the energy of the photon minus the energy of the dissociation, and we'd find that our excess energy is 2.93 times 10 to the negative 19th joules. Now on to part C, we have to use our knowledge of this energy and wavelength to calculate the kinetic energy. So first we need to know the mass of hydrogen, which is 1.6735 times 10 to the negative 27th kilograms. And the equation for kinetic energy is 1/2 times mv squared. M is our mass, and v is essentially our velocity or speed. So kinetic energy will be 1/2 times the mass of hydrogen, 1.6735 times 10 to the negative 23rd kilograms. We'll multiply that by v squared, which is equivalent to our energy that we just calculated, 2.93 times 10 to the negative 19th joules. Then we find v, so we would move all of this number onto our right side of equation, take the square root, and we'll find that v is 1.87 times 10 to the 4th meters per second, and that is our speed. So I hope that this problem helped you understand how we can use concepts like bond energy to find the wavelength of a sample, then use the wavelength to find the energy of a photon and the excess energy, and then finally we can use all of these things combined to find kinetic energy.